So as a quick recap, last time we talked about activation functions. We talked about this whole zoo of different activation functions and some of their different properties. We saw that the sigmoid, which used to be quite popular when training neural networks maybe 10 years ago or so, has this problem with vanishing gradients near the two ends of the activation function. TANH has this similar sort of problem. And kind of the general recommendation is that you probably want to stick with ReLU for most cases as sort of a default choice, because it tends to work well for a lot of different architectures. We also talked about weight initialization. And remember that up on the top, we have this idea that if when you initialize your weights at the start of training, if those weights are initialized to be too small, then if you look at then the activations will vanish as you go through the network. Because as you multiply by these small numbers over and over again, they'll all sort of decay to 0. And then everything will be 0, learning won't happen, you'll be sad. On the other hand, if you initialize your weights too big, then as you go through the network and multiply by your weight matrix over and over again, eventually they'll explode, you'll be unhappy, there'll be no learning, it will be very bad. But if you get that initialization just right, for example, using the Xavier initialization or the MSRA initialization, then you kind of keep a nice distribution of activations as you go through the network. And remember that this kind of gets more and more important and more critical as your networks get deeper and deeper, because as your network gets deeper, you're multiplying by those weight matrices over and over again with these more multiplicative terms. We also talked last time about data pre-processing. We talked about how it's pretty typical in ConvNets to zero center and normalize your data, so it has zero mean and unit variance. I wanted to provide a little bit of extra intuition about why you might actually want to do this. So imagine a simple setup where we have a binary classification problem where we want to draw a line to separate these red points from these blue points. So on the left, you have this idea where if those data points are kind of not normalized and not centered and far away from the origin, then we can still use a line to separate them. But now if that line wiggles just a little bit, then our classification is going to get totally destroyed. And that kind of means that in the example on the left, the loss function is now extremely sensitive to small perturbations in that linear classifier in our weight matrix. And so we can still represent the same functions, but that might make learning quite difficult because, again, our loss is very sensitive to our parameter vector. Whereas if in the situation on the right, if you take that data cloud and you move it into the origin and you make it unit variance, then now again, we can still classify that data quite well, but now as we wiggle that line a little bit, then our loss function is less sensitive to small perturbations in the parameter values. And that maybe makes optimization a little bit easier, as we'll see a little bit going forward. And by the way, this situation is not only in the linear classification case. Inside a neural network, remember, we kind of have these interleavings of these linear matrix multiplies or convolutions, followed by nonlinear activation functions. And if the input to some layer in your neural network is not centered or not zero mean, not unit variance, then again, small perturbations in the weight matrix of that layer of the network could cause large perturbations in the output of that layer, which again might make learning difficult. So this is kind of a little bit of extra intuition about why normalization might be important. And because we have this intuition that normalization is so important, we talked about batch normalization, which is where we just add this additional layer inside our networks to just force all of the intermediate activations to be zero mean and unit variance. And I've sort of re-summarized the batch normalization equations here with the shapes a little bit more explicitly. Hopefully this can help you out when you're implementing this thing on assignment 2. But again, in batch normalization, we have this idea that in the forward pass, we use the statistics of the mini batch to compute a mean and a standard deviation, and then use those estimates to normalize our data on the forward pass. And then we also reintroduce these scale and shift parameters to increase the expressivity of the layer. So you might want to refer back to this when working on assignment 2. We also talked last time a little bit about babysitting the learning process, how you should probably be looking at your loss curves during training. So here's an example of some networks I was actually training over the weekend. And this is usually my setup when I'm working on these things. On the left, I have some plot showing the training loss over time. And you can see it's kind of going down, which means my network is reducing the loss. It's doing well. And on the right, there's this plot where the x-axis is, again, time, or the iteration number, and the y-axis is my performance measure both on my training set and on my validation set. And you can see that as we go over time, then my training set performance goes up and up and up and up and up as my loss function goes down. But at some point, my validation set performance kind of plateaus. So this kind of suggests that maybe I'm overfitting in this situation. Maybe I should have been trying to add additional regularization. We also talked a bit last time about hyperparameter search. All these networks have sort of a large zoo of hyperparameters, and it's pretty important to set them correctly. We talked a little bit about grid search versus random search, and how random search is maybe a little bit nicer in theory because in the situation where your performance might be more sensitive with respect to one hyperparameter than another, and random search lets you cover that space a little bit better. We also talked about the idea of coarse-to-fine search, where when you're doing this hyperparameter optimization, probably you want to start with a very wide ranges for your hyperparameters, only train for a couple iterations, and then based on those results, you kind of narrow in on the range of hyperparameters that are good, and now, again, redo your search in a smaller range for more iterations. And you can kind of iterate this process to kind of hone in on the right region for hyperparameters. But again, it's really important to, at the start, have a very coarse range to start with, where you want very, very wide ranges for all your hyperparameters. And ideally, your network those ranges should be so wide that your network is kind of blowing up at either end of the range, so that you know that you've searched a wide enough range for those things. The question is, how many hyperparameters do you typically search at a time? Here is 2, but there's a lot more than 2 in these typical things. So it kind of depends on the exact model and the exact architecture, but because the number of possibilities is exponential in the number of hyperparameters, you can't really test too many at a time. It also kind of depends on how many machines you have available. So it kind of varies from person to person and from experiment to experiment. But generally, I try not to do this over more than maybe 2 or 3 or 4 at a time at most. Because again, this exponential search just gets out of control. So typically, learning rate is the really important one that you need to nail first. And then other things like regularization, like learning rate decay, model size, these other types of things tend to be a little bit less sensitive than learning rate. So sometimes you might do kind of a block coordinate descent, where like you go and find the good learning rate, then you go back and try to look at different model sizes. And this can help you cut down on the exponential search a little bit. But it's a little bit problem dependent on exactly which ones you should be searching over in which order. Yeah, question is, how often does it happen where when you change one hyperparameter, then the optimal values of the other hyperparameters change? That does happen sometimes, although for learning rates, that's typically less of a problem. So for learning rates, typically you want to get in a good range and then set it maybe even a little bit lower than optimal and let it go for a long time. And then if you do that, combined with some of the fancier optimization strategies that we'll talk about today, then a lot of models tend to be a little bit less sensitive to learning rate once you get them in a good range. The question is, what's wrong with having a small learning rate and increasing the number of epochs? The answer is that it might take a very long time. So intuitively, if you set the learning rate very low and let it go for a very long time, then this should, in theory, always work. But in practice, those factors of 10 or 100 actually matter a lot when you're training these things. So maybe if you got the right learning rate, you could train it in 6 hours, 12 hours, or a day. But then if you just were super safe and dropped it by a factor of 10 or by a factor of 100, now that 1 day training becomes 100 days of training. That's 3 months. That's not gonna be good. So this is one of those. So when you're taking these intro computer science classes, they always kind of sweep the constants under the rug. But when you're actually thinking about training things, those constants end up mattering a lot. Question is, for low learning rate, are you more likely to be stuck in local optima? I think that makes in some intuitive sense, but in practice, that seems not to be much of a problem. And I think we'll talk a bit more about that later today. OK, so today I wanted to talk about a couple other really interesting and important topics when we're training neural networks. In particular, I wanted to talk, so we've kind of alluded to this fact of fancier, more powerful optimization algorithms a couple times. I wanted to spend some time today and really dig into those and talk about what are the actual optimization algorithms that most people are using these days. We also touched on regularization in earlier lectures, this concept of making your network do additional things to reduce the gap between train and test error. And I wanted to talk about some more strategies that people are using in practice of regularization with respect to neural networks. And finally, I also wanted to talk a bit about transfer learning, where you can sometimes get away with using less data than you think, by transferring from one problem to another. So if you recall from a few lectures ago, the kind of core strategy in training neural networks is an optimization problem, where we write down some loss function, which defines, for each value of the network weights, the loss function tells us how good or bad is that value of the weights doing on our problem. And then we imagine that this loss function gives us some nice landscape over the weights, where on the right, I've shown this maybe small two-dimensional problem, where the x and y axes are two values of the weights, and then the color of the plot kind of represents the value of the loss. So in this kind of cartoon picture of a two-dimensional problem, we're only optimizing over these two values, W1, W2, and the goal is to find the most red region in this case, which corresponds to the setting of the weights with the lowest loss. And remember, we've been working so far with this extremely simple optimization algorithm, stochastic gradient descent, where we have it's super simple, it's 3 lines. While true, we first evaluate the loss and the gradient on some mini batch of data, and then we step updating our parameter vector in the negative direction of the gradient, because this gives, again, the direction of greatest decrease of the loss function. And then we repeat this over and over again, and hopefully we converge to the red region, and we get great errors, and we're very happy. But unfortunately, this relatively simple optimization algorithm has quite a lot of problems that actually could come up in practice. So one problem with stochastic gradient descent, imagine what happens if our objective function looks something like this, where again we're plotting two values, W1 and W2, and as we change one of those values, the loss function changes very slowly. As we change the horizontal value, then our loss changes slowly. As we go up and down in this landscape, now our loss is very sensitive to changes in the vertical direction. So by the way, this is referred to as the loss having a bad condition number at this point, which is the ratio between the largest and smallest singular values of the Hessian matrix at that point. But the intuitive idea is that the loss landscape kind of looks like a taco shell, and it's sort of very sensitive in one direction, not sensitive in the other direction. So the question is, what might SGD, stochastic gradient descent, do on a function that looks like this? So if you run stochastic gradient descent on this type of function, you might get this characteristic zigzagging behavior, where because for this type of objective function, the direction of the gradient does not align with the direction towards the minima. So when you compute the gradient and take a step, you might step sort of over this line and sort of zigzag back and forth. So in effect, you get very slow progress along the horizontal dimension, which is the less sensitive dimension, and you get this zigzagging, nasty zigzagging behavior across the fast-changing dimension. And this is undesirable behavior. And by the way, this problem actually becomes much more common in high dimensions, right? So in this kind of cartoon picture, we're only showing a two-dimensional optimization landscape. But in practice, our neural networks might have millions, tens of millions, hundreds of millions of parameters. So that's hundreds of millions of directions along which this thing can move. And now, among those hundreds of millions of different directions to move, if the ratio between the largest one and the smallest one is bad, then SGD will not perform so nicely. And you can imagine that if we have 100 million parameters, probably the maximum ratio between those two will be quite large. So I think this is actually quite a big problem in practice for many high-dimensional problems. Another problem with SGD has to do with this idea of local minima, or saddle points. So here, I've sort of swapped the graph a little bit, and now the x-axis is showing the value of one parameter, and then the y-axis is showing the value of the loss. So in this top example, we have kind of this curvy objective function where there's a valley in the middle. And what happens to SGD in this situation? Yeah, so in this situation, SGD will get stuck because at this local minima, the gradient is 0 because it's locally flat. And now remember, with SGD, we compute the gradient and step in the direction of opposite gradient. So if at our current point the opposite gradient is 0, then we're not going to make any progress and we'll get stuck at this point. There's another problem with this idea of saddle points. Rather than being a local minima, you can imagine a point where in one direction we go up and in the other direction we go down, and then at our current point the gradient is 0. And again, in this situation, the function will get stuck at the saddle point because the gradient is 0. Although one thing I'd like to point out is that in a one-dimensional problem like this, local minima seem like a big problem, and saddle points seem like kind of not something to worry about. But in fact, it's the opposite once you move to very high-dimensional problems. Because again, if you think about you're in this 100 million dimensional space, what does a saddle point mean? That means that at my current point, some directions the loss goes up, and some directions the loss goes down. And if you have 100 million dimensions, that's probably going to happen more frequently that's probably going to happen almost everywhere, basically. Whereas a local minima says that of all those 100 million directions that I can move, every one of them causes the loss to go up. And in fact, that seems pretty rare when you're thinking about, again, these very high-dimensional problems. And so really, the idea that has come to light in the last few years is that when you're training these very large neural networks, the problem is more about saddle points and less about local minima. And by the way, this also is a problem not just exactly at the saddle point, but also near the saddle point. So if you look at the example on the bottom, you see that in the regions around the saddle point, the gradient isn't 0, but the slope is very small. And that means that if we're, again, just stepping in the direction of the gradient, and that gradient is very small, we're going to make very, very slow progress whenever our current parameter value is near a saddle point in the objective landscape. So this is actually a big problem. So another problem with SGD comes from the S. So remember that SGD is stochastic gradient descent. So recall that our loss function is typically defined by computing the loss over many, many different examples. But in this case, n, if n is your whole training set, then that could be something like 1 million. So each time computing the loss would be very, very expensive. So in practice, remember that we often estimate the loss and estimate the gradient using a small mini batch of examples. What this means is that we're not actually getting the true information about the gradient at every time step. Instead, we're just getting some noisy estimate of the gradient at our current point. So here on the right, I've kind of faked this plot a little bit. So I've just added random uniform noise to the gradient at every point, and then run SGD with these noisy, messed up gradients. And so this is maybe not exactly what happens with the SGD process, but it still gives you this sense that if there's noise in your gradient estimates, then vanilla SGD kind of meanders around the space. And it might actually take a long time to get towards the minima. Yeah, so the question is, do all of these just go away if we use normal gradient descent? So let's see. So I think that the taco shell problem of high condition numbers is still a problem with full batch gradient descent. The noise, as we'll see, we might sometimes introduce additional noise into the network, not only due to sampling mini batches, but also due to explicit stochasticity in the network. So we'll see that later. So that can still be a problem. And saddle points, that's still a problem for full batch gradient descent because there can still be saddle points in the full objective landscape. So basically, even if we go to full batch gradient descent, it doesn't really solve these problems. So we kind of need to think about a slightly fancier optimization algorithm that can try to address these concerns. So thankfully, there's a really, really simple strategy that works pretty well at addressing many of these problems, and that's this idea of adding a momentum term to our stochastic gradient descent. So here on the left, we have our classic old friend, SGD, where we just always step in the direction of the gradient. But now on the right, we have this minor, minor variant called SGD plus momentum, which is now 2 equations and 5 lines of code. So it's like twice as complicated. But it's very simple. The idea is that we maintain a velocity over time, and we add our gradient estimates to the velocity, and then we step in the direction of the velocity rather than stepping in the direction of the gradient. So this is very, very simple. And we also have this hyperparameter rho now, which corresponds to friction. So now at every time step, we take our current velocity, we decay the current velocity by the friction constant, rho, which is often something high, like 0.9 is a common choice. Then we take our current velocity, we decay it by friction, and we add in our gradient. And now we step in the direction of our velocity vector rather than the direction of our raw gradient vector. And this super, super simple strategy actually helps for all of these problems that we just talked about. So if you think about what happens at local minima or saddle points, then if we're imagining velocity in this system, then you kind of have this physical interpretation of this ball kind of rolling down the hill, picking up speed as it comes down. And now once we have velocity, then even when we pass that point of local minima, the point will still have velocity even if it doesn't have gradient. So then we can hopefully get over this local minima and continue downward. There's this similar intuition near saddle points, where even though the gradient around the saddle point is very small, we have this velocity vector that we've built up as we roll downhill, and that can hopefully carry us through the saddle point and let us continue rolling all the way down. If you think about what happens in poor conditioning, now if we were to have these kind of zigzagging approximations to the gradient, then those zigzags will hopefully cancel each other out pretty fast once we're using momentum, and this will effectively reduce the amount by which we step in the sensitive direction, whereas if in the horizontal direction, our velocity will just keep building up and will actually accelerate our descent across that less sensitive dimension. So adding momentum here can actually help us with this high condition number problem as well. Finally, on the right, we've repeated the same visualization of gradient descent with noise. And here the black is this vanilla SGD, which is sort of zigzagging all over the place, where the blue line is showing now SGD with momentum. So you can see that because we're building up this velocity over time, the noise kind of gets averaged out in our gradient estimates. And now SGD ends up taking a much smoother path towards the minima compared with the SGD, which is kind of meandering due to noise. The question is, how does SGD momentum help with the poorly conditioned coordinate? So the idea is that if you go back and look at this velocity estimate and look at this velocity computation, we're adding in the gradient at every time step. So I mean, it kind of depends on your setting of rho, that hyperparameter. But you can imagine that if the gradient is relatively small and if rho is well behaved in this situation, then our velocity could actually monotonically increase up to a point where the velocity could now be larger than the actual gradient. So then we might actually make faster progress along the poorly conditioned dimension.
이번 시간에는 뉴럴 네트워크 트레이닝의 파트 2에 대해서 강의하도록 하겠습니다. 지난 시간에는 6가지 액티베이션 펑션과 이들의 장단점에 대해서 배웠습니다. 이 중에서 렐루가 간단하면서도 좋은 퍼포먼스를 내기 때문에 많은 아키텍처에서 사용되고 있습니다. Wait Initialization, 초기화에 대해서 배웠는데 Initialization이 너무 작게 되면 액티베이션이 0으로 가고 그라디언트도 0으로 가면서 학습이 진행이 안 된다는 것을 말씀드렸습니다. 반면에 Initialization이 너무 큰 경우 액티베이션이 Saturate 되고 그라디언트는 0으로 가면서 역시 학습이 되지 않습니다. Initialization이 잘 된 경우 맨 아래 그림에서 보듯이 모든 레이어에서 액티베이션의 디스트리뷰션이 잘 되어 있습니다. 이 경우 학습도 잘 진행이 됩니다. 데이터 프리프로세싱에서는 오리지널 데이터를 제로 센터 데이터로 이동하고 노멀라이즈 데이터로 스케일하는 것에 대해서 말씀드렸습니다. 왼쪽 그림에 있는 것처럼 노멀라이제이션을 하기 전에는 클래시피케이션 로스가 웨이트 매트릭스의 변화에 매우 민감하고 옵티마이즈를 하기가 어렵습니다. 반면에 오른쪽 그림에 있는 것처럼 노멀라이제이션을 하고 난 다음에는 작은 웨이트의 변화에 덜 민감하고 옵티마이즈를 하기가 더 용이합니다. 배치 노멀라이제이션은 레이어를 추가해서 이너미디엇 액티베이션이 제로민과 유닛 베리언스를 갖도록 하는 것입니다. 이 값의 감마를 곱하고 베타를 더해서 아웃풋 y를 만들어냄으로써 레이어의 표현성을 증가시킨 것입니다. 이때 감마와 베타는 러너블 파라미터, 학습되는 파라미터들입니다. 러닝을 관리하는 것에 대해서도 배웠는데 트레인 로스 그래프에서는 이터레이션 혹은 시간이 지남에 따라서 로스가 줄어드는 것을 볼 수 있습니다. 또한 accuracy는 시간의 지남에 따라서 train accuracy, validation accuracy가 증가하는 것을 볼 수 있습니다. 그런데 validation accuracy는 어떤 지점이 지나면 plateau, 평지가 되면서 더 이상 증가하지 않습니다. 이 경우에 overfitting의 가능성이 있기 때문에 플래토가 시작하기 전까지만 트레이닝하는 것이 좋습니다. 이때 regularization을 약간씩 증가시키면서 러닝 프로세스를 관리할 수도 있습니다. 하이퍼 파라미터 서치는 학습에서 중요한 부분입니다. 그리드 방식이 있고 랜덤 방식이 있는데 그리드 방식은 특정 데이터 형태에 잘 동작하기 때문에 랜덤 방식이 더 선호됩니다. 파라미터를 찾는 방법은 coarse to fine search입니다. 처음에는 coarse하게 넓은 레인지를 찾고 다음에는 fine하게 작은 레인지를 찾아서 점점 좁혀나갑니다. 다음은 좀 더 팬시한 옵티마이제이션과 regularization 그리고 트랜스퍼 러닝에 대해서 배우도록 하겠습니다. 뉴럴 네트워크의 코어 스트래티지는 옵티마이제이션 문제입니다. 로스 펑션은 현재 우리가 가진 웨이트가 주어진 문제를 얼마나 잘 풀고 있는지를 보여줍니다. 오른쪽 그림은 웨이트에 대한 랜드스케이프를 보여주고 있는데 빨간색으로 갈수록 로스 값이 작아지는 것을 의미합니다. 이 경우에 옵티마이제이션 문제는 W1과 W2를 조정해서 가장 로스가 낮은 지점, 즉 빨간 지점에 도달하도록 하는 것입니다. 왼쪽에 세 줄로 옵티마이제이션이 코딩된 것을 볼 수 있습니다. while loop에서 그라디언트의 웨이트를 구한 뒤 이를 스텝 사이즈에 곱해서 웨이트를 업데이트합니다. 이때 하강하는 경사 방향을 그라디언트의 네거티브 디렉션이라고 합니다. 이러한 스텝을 계속 반복해서 빨간 지역에 도달하는 것을 희망하는 것입니다. 이러한 스토캐스틱 그레디언트 디센트 방법의 문제점들을 알아보도록 하겠습니다. 예를 들어서 로스의 값이 수평 방향으로 천천히 변하고 수직 방향으로는 빠르게 변할 수 있습니다. 이 경우에 수평 방향으로 느린 프로그레스가 나타나고 수직 방향으로는 지터 현상이 나타날 수 있습니다. 두 번째로 SGD는 로스 펑션이 로컬 미니마 혹은 새들 포인트를 가질 때 잘 동작하지 않을 수 있습니다. 로컬 미니마에서 그레디언트 값이 제로가 되기 때문에 이 상태에서 빠져나오기가 어렵습니다. 이러한 새들 포인트는 하이 디멘전에서 흔히 발생합니다. 또 다른 문제는 그레디언트 값들이 미니 배치에서 나오기 때문에 노이즈할 수 있다는 것입니다. 오른쪽 그림을 보면 노이즈의 결과로 스텝이 매끈하지 않은 것을 알 수 있습니다. 다행히도 스토캐스틱 그레디언트 디센트의 문제들을 해결하는 방법이 있는데 모멘텀을 더하는 것입니다. 왼쪽의 SGD 방식에서는 그레디언트 디렉션의 방향으로 위치를 변화시킵니다. 반면에 SGD 플러스 모멘텀 방식에서는 속도의 변화를 먼저 계산한 뒤 이를 바탕으로 위치의 변화를 계산합니다. 이 식의 함축된 의미는 우리가 그라디언트의 디렉션 방향으로 움직이는 것이 아니라 벨로시티의 방향으로 움직인다는 것입니다. SGD 모멘텀에서는 하이퍼 파라미터 로우가 추가됐는데 프릭션을 의미합니다. 대개 0.9나 0.99 정도의 값을 가집니다. 이러한 매우 간단한 방법이 SGD의 문제점을 해결하는데 큰 도움을 줄 수 있습니다. SGD의 문제점이었던 로컬 미니마나 새들 포인트의 경우에 언덕을 내려오는 공의 비율을 든다면 벨로시티를 갖고 있기 때문에 로컬 미니마나 새들 포인트에서 속도가 느려지기는 해도 이를 지나쳐가기 때문에 이러한 점들을 극복할 수 있습니다. 풀 컨디셔닝의 경우에도 수직과 수평 방향으로 속도가 갑자기 변할 수 없기 때문에 지터 모양보다는 부드러운 궤적 모양이 좀 더 그려지게 됩니다. 오른쪽 그림에서 까만 선은 바닐라 SGD를 나타내고 파란 선은 SGD 플러스 모멘텀을 나타냅니다. 파란 선이 까만 선보다 더 효율적으로 더 빠르게 로스 미니멈에 도달하는 것을 볼 수 있습니다.